So that we determined was 4.3 times 10 to the minus 4 molar. To put in our our oxalate concentration of 4. So we can use our KSP again for calcium oxalate. And that's 2.3 times 10 to the minus 9. That's going to be equal to our calcium concentration times the oxalate concentration. And to determine how much calcium is present when the magnesium oxalate begins to precipitate, we need 3 times 10 to the minus 4 molar. Everyone see that? That's a little bit tricky, I think. And so we can solve for calcium ion. And we'll get a concentration of calcium ion of 5.3 times 10 to the minus 6 molar. So once that magnesium oxalate starts precipitating, we're essentially saying we're not precipitating any more calcium. But we still have calcium ion in solution because there is an equilibrium with the solid that remains in the solution, remains in the beaker or whatever. So that concentration is going to be this value. Small, but measurable, okay? And if we look at a percentage that's left, we started with 0.2 molar. Oops. Now we're left with 5.3 times 10 to the minus 6 molar. If we figure out the percent, that's only 2.6 times 10 to the minus 3% that's remaining in solution. So it's a really small fraction of the initial concentration, but there is some in there. Questions on that? Okay. Let's now take a look at how other factors affect the solubility of various salts. So sometimes we form ions with dissolving solids that then can react with water and form H3O plus or OH minus. Right? Other times we can add acid or base to a solution to increase solubility. Right? And that's what I'm going to show here in this example. This is our calcium oxalate. Okay? We know what its equilibrium looks like. It has a KSP value associated with it. But oxalate ion is the conjugate base of oxalic acid. So that's what this, well, actually that's only one proton. So oxalic acid is H2C2O4. So if we were to add acid to a beaker that contains calcium oxalate, what would you expect to happen to the solubility of the calcium oxalate? Increase or decrease? So decrease? Everyone agree? So what we should expect to happen when we add acid is that it's going to react with our oxalate ion and reduce this concentration, thereby pushing the equilibrium towards the product side of this reaction. Which means that the calcium oxalate will be more soluble in an acidic solution. So the equilibrium in equation 1 shifts towards the products, and so calcium oxalate is more soluble in acidic solution than in pure water. Okay? Everyone see that? So our calcium oxalate example, Oh yeah. So we can go on and you can figure out equilibria and concentrations of acid or base that would increase or decrease the solubility. We never really calculate decrease solubility for various salts. But if you're looking at more of a qualitative effect, the first thing you'll want to do, like we did here in our so we write out the equilibrium for the solubility, so the KSP expression. And then you can write the reaction of the affected ion that reacts with acid or base, depending on which you're adding. And that's going to be another K, Ka, or Kb, depending. Okay? And that should help you determine which direction the reaction is going to shift in order to regain equilibrium. So let's look at calcium carbonate. Okay? Calcium carbonate is a solid. When you put it in solution, has a small KSP. Can you see that? Yeah. 3.4 times 10 to the minus 9. But it will form some calcium ion and some carbonate ion. But carbonate can react with acid, H+, to form H2CO3, carbonic acid. Okay? When this second reaction happens, what do you think happens to the solubility of calcium carbonate? Increases or decreases? It's going to increase, right? So let's try. So calcium carbonate is chalk. So I've got 2 beakers with chalk. In this beaker, I'm going to put distilled water. Okay. That's going to essentially give us our first equation. And then in this beaker, I'm going to put 6 molar hydrochloric acid. So I am going to pseudo for that. Actually, let's do it this way. It's more fun if you drop them. All right, so there's our water. There's our acid. There's our vent. Okay, you ready? 1, 2, 3. So the foaming is the dissolution, forming carbonic acid. Carbonic acid then degrades to form carbon dioxide, so it's actually kind of a fun reaction. We'll let this go a while. You know, you can see that the chalk is bubbling there. And this chalk is not doing anything, essentially. Okay. So there's a drastic increase here in our solubility, right? I mean, visually, you can even see it. All right. Plus, there's no trash. All right, this is not going. Questions on that? Okay. There will be some calculations that you'll be expected to do with pH and solubility. I'm going to skip over those for now. If we have time later on, we can come back to them, but I want to make sure we get to this next topic, which is a little bit more challenging. So, this is we're going to talk about complex ion equilibrium. So we're going to look at the formation of complex ions. Complex ions, at least the ones that we're going to be thinking about, generally are more soluble than the salt from which they are made. So what we're going to do is react some metal ions with a Lewis base, form a coordinate covalent bond, and form what's known as a complex ion. So if you don't remember coordinate covalent bonds, that's okay. It's a bond formed when both electrons are donated by one atom. And so you can see that here with ammonia, NH3. We have 2 electrons, a lone pair. The ammonia is going to donate those electrons to silver to form a bond between the nitrogen and the silver. Okay, that's a coordinate covalent bond. When we are writing out formula, you'll notice that they will have an overall charge. So an even smoother way of writing the silver ammonia complex is Ag NH3. You're more likely to see this than what I have written there, but I wanted to show you the bonds. Put that in brackets, and then the +1 charge at the top. So in this case, silver acts as a Lewis acid, and the ammonia acts as a Lewis base. Okay, but you'll notice we have an equilibrium, which means we're going to have a K value associated with that. Given by this equation shown here, here's K sub F, so we're forming that complex ion. We're actually going to have 2 K values that we're going to end up using. We're going to have K sub F for the formation of the complex ion. So that would, and we're also going to use K sub D, the dissociation constant. So that's the reverse reaction. So that would be the silver and AgNH3 2 plus in equilibrium with Ag plus and 2NH3. Everything in this equation reaction is aqueous, by the way. Okay. And so since we've reversed the reaction, we're reversing a reaction between Kd and K sub F, the relationship of the K values are the inverse. So K sub F, the formation constant, is 1.7 times 10 to the minus 7. K sub D is equal to 1 over K sub F. And that's given here 5.9 times 10 to the minus 8 for this complex. Your book has a table with various complex ions that can form and their associated Kf or Kd values, maybe both, I can't remember. But it's all tabulated, so you can find those. So let's start doing some problems, because these are pretty challenging. So we're going to take 0.1 molar nickel nitrate. Nitrates are soluble. We're going to dissolve that in 1 liter of water that also contains 1 mole of sodium cyanide. What is the concentration of nickel in solution after it comes to equilibrium and forms this complex ion? Okay. So this is going to be a multi-step problem. And in the first step, we're going to make an assumption. We're going to assume that when we mix everything, that the nickel is going to react completely and form the complex ion. And we're going to work that out on the next slide. After that, we know that that's not real. We know it's not going to completely react. But it's going to allow us to have sort of a basis for our calculation where we look at the dissociation of that complex ion and determine how much nickel is going to be remaining in solution after what we have assumed all of that complex ion is formed after that dissociates. And so we're going to use our Kd value here. Okay. First thing, assume that the nickel reacts completely to form the complex ion. So I'm just going to rewrite the equation to represent the assumption. Nickel 2 plus 4Cn minus is going to form the complex ion. Okay. And now we're going to use a reaction table or a BCA table. Okay, so our before moles, we're going to have 0.1 moles of nickel given in the problem. We have available to us 1 mole of Cn minus. Okay, so we have 1 mole of NaCN. That's going to completely dissociate. And initially, in our before line, we have 0 of the complex ion. Now, in these types of problems, you're going to have to make sure you pay extra attention to the stoichiometry. There's always going to be some crazy big number here, pretty much. Maybe 2, 4, 6, those are common. So the change, this is a limiting reagent problem, okay? Much like we were doing with our reaction tables in the titration types of calculations. We are going to be limited in this case by the nickel, okay? We have 0.1 molar of that. If we are going to react 0.1 moles of the nickel, how many moles of the Cn minus are going to react? 0.4. Good. Okay. Okay, so it's 4 times 0.1. So for every 1 nickel, there's going to be 4 Cn minus. And we're going to form 0.1 of the complex. So after, we'll have 0 moles of the nickel. We're going to have 0.6 moles of the Cn minus, and we're going to have 0.1 moles of the complex ion. So now we're going to have a solution that contains it's going to contain 0.1 moles of the nickel complex, and it's 1 liter, so it's actually 0.1 moles per liter. We can go ahead and write that there. And we're going to have 0.6 moles of Cn minus. No moles of nickel. We're assuming it reacts completely. Everyone okay here? Okay. Now we're going to acknowledge the fact that that isn't actually going to happen. It's easier to go this way, make the assumption first, and go back than it is to go forward, mathematically. So now we're going to use the equilibrium for the dissociation of the nickel complex. So we'll have NiCN for 2 minus, aqueous, in equilibrium with the nickel 2 plus. Oops, this is supposed to be 2. Oh yeah, 2 minus, that's right. Plus 4 Cn minus. And now we're going to use an ice table. So we're going to have initial concentrations of the complex. That's the 0.1 moles per liter. Again, we're using molarity here. 0 moles per liter of the nickel ion, and 0.6 moles per liter of Cn minus. When the nickel dissociates, we're going to lose some amount X of the complex ion. We're going to form some amount X of the nickel, and we're going to form plus 4X for Cn minus. Again, the stoichiometry. Okay? So at equilibrium, we're going to have 0.1 minus X for the nickel complex, X moles per liter of the nickel ion, and 0.6 plus 4X for Cn minus. Okay, we were given a Kf value Okay, that's for the formation of the complex ion. But now we're looking at the dissolution. So we need our Kd value, and that's 1 over the Kf value. Kf was 1 times 10 to the minus 31. K sub d is going to be 1 times 10 to the minus 31. Okay, and we can fill out the rest of our equilibrium constant expression. We're going to have the concentration of nickel ion times the concentration of Cn minus, and this is going to be raised to the power of 4, divided by the nickel complex concentration. Okay, watch that you don't put the charge outside and then think that you need to raise it to that power. That's another little thing to pay attention to there. So if we plug in our equilibrium concentrations that are in terms of X from our ice table, we'll have X moles per liter from the nickel, 0.6 plus 4X raised to the 4th for Cn minus, and 0.1 minus X for the complex ion. All right, everyone okay there so far? Okay. So what we're going to do now, notice how tiny our Kd value is, times 10 to the minus 31. Very little of this is going to dissociate. And so what that means is that we're going to assume the X is small. Combine that into one word there, that's nice. So we can cross out X in comparison to the 0.1 and the 4X in comparison to the 0.6. Okay. So now we're left with 1 times 10 to the minus 31 is equal to X times 0.6 raised to the 4th divided by 0.1. And what we end up with is X is equal to 7.7 times 10 to the minus 32. Really, really small. That's going to be the concentration of nickel, 2+. Okay. Does that make sense? That's our X. That's in our ice table. The trickiest part with these problems is the concept that you have to assume the reaction occurs to completion and then do the dissolution with the equilibrium. Okay? It's a two-stepper. Questions on that? All right. So let's continue looking at how complex ions affect solubility. So we'll look at silver chloride. It's an insoluble salt. KSP is 1.8 times 10 to the minus 10. So if we take a saturated solution of silver chloride and we use our KSP, it's going to be equal to the silver ion concentration times the chloride ion concentration, and that's 1.8 times 10 to the minus 10. Take the square root of that to get the concentration of silver and chloride in solution, 1.3 times 10 to the minus 5. Okay? So small concentrations. Yes, it's very insoluble. What happens then if we add ammonia to a saturated solution of silver chloride? What do you expect to happen to the solubility? Increase, decrease? What's that? So we're going to add ammonia to a solution of silver chloride. I know what's going to happen to the concentration. And we've got number 2 here. Silver ion can react with the ammonia to form the complex ion. So what happens to the solubility of silver chloride? It's going to increase, right? So whenever we add a complex ion to an insoluble salt, if it can form whenever we add a ligand or a Lewis base to a solution of a insoluble salt, if it can form a complex ion, it will increase the solubility of that salt. Okay? So this adding ammonia is common. There are a number of other ones as well. Cn minus, as we just saw. Okay. So our solubility is going to increase. This is again just the Chatelier's principle. That's repeating itself over and over here with our equilibria. We've done this previously without all of this complex ion stuff. Just as that reminder, we did this here on the previous slide, figuring out the molar solubility for silver chloride. That's the X in the ice table. So that's the 1.3 times 10 to the minus 5 when there's no ammonia in solution. Okay? Calculate when there's no ammonia, 1.3 times 10 to the minus 5. Okay, so let's actually look at the effect on the molar solubility of silver chloride. So let's imagine what's happening in solution. We have a beaker. We said we had saturated silver chloride. So maybe at the bottom of the beaker, we have some solid silver chloride. Okay? And in the solution, we do have silver ions and chloride ions. Small amount, but they're there. Now we're going to add in ammonia, NH3. Okay, and we just saw that we're going to expect the solubility of silver chloride to increase. So we should get more silver ions into solution. Those silver ions are going to react with the ammonia. Okay. So really what we have going on in solution are 2 equilibria. The first equilibria is associated with the KSP. So that's our solid silver chloride in equilibrium with the component ions, silver ion, chloride ion. Then we also have the silver ion reacting with the ammonia molecule to form the complex ion. And this is going to have a case of F associated with it. These values, again, you would look up. And we will get to that. But because both of these equilibria are occurring simultaneously in solution, we can essentially add them up. Okay? And so in doing that, you've done this before, it's no different than before. We'll cancel out any ions that appear on the reactant side of one and the product side of another. So silver we can cross out. Now we're going to have, as an overall equilibrium, silver chloride solid plus 2 ammonia. I'm just going to write 2 NH3, leave off the dots. That's aqueous. In equilibrium with chloride ion and the complex ion. Ag, NH3, 2 with a +1 charge. So how do we find the K for this equilibrium? Back to chapter 15. We multiply. All right, so we're going to multiply, so we'll do K overall is going to be equal to KSP times K sub F. And for this equilibrium, KSP is 1.8 times 10 to the minus 10. K sub F is 1.7 times 10 to the 7th. And so K overall is equal to 3.1 times 10 to the minus 3. Okay. Everyone good so far? This is complicated. It will come back to haunt you. Warning. This overall expression is going to allow us to look at this third equilibrium, the overall equilibrium, and figure out the molar solubility now of the silver chloride with the ammonia. Okay, that's what that equilibrium is telling us. Okay, so we can set up an ice table. We want to figure out the molar solubility of silver chloride. So now we're going to set up our ice table with the overall expression AgCl solid plus 2NH3 aqueous in equilibrium with AgNH3 2, there's a 2 there, plus Cl minus. Okay. So we'll do our ice table. Initial concentrations. So we've got a solid, we've got silver chloride. We don't need to worry about solids in our ice tables. So I'm just going to draw a line to remind myself, stop caring. Okay. Now we have an initial concentration of ammonia. And we said it's 1 mole per liter in our solution. So that'll go there. Initially, we don't have any complex formed and no chloride ion. So in terms of the change, we're going to have minus 2x for the ammonia, again the stoichiometry, plus x for the complex ion, and plus x for chloride ion. So at equilibrium, we'll have 1 minus 2x for NH3, x moles per liter of the complex ion, and x moles per liter of chloride ion. And now we can plug this into our equilibrium constant expression. We said that K overall was equal to 3.1 times 10 to the minus 3. This is going to be equal to the concentration of products over the reactants. So we'll have x squared over 1 minus 2x, and that's squared as well, don't forget that. What's special about this equation? What's that? It's a perfect square, yes. So we can take the square root of both sides. If it wasn't a perfect square, now this K value is actually kind of big, so we probably couldn't assume that x was small, so you might have to go through and do the quadratic. That's an exceptionally ugly one. Keep an eye out for the perfect square. The other thing is, depending on the K value, you might be able to assume that x is small in relation to a number. Okay. So we're going to take the square root of both sides. And we will have 0.056 is equal to x over 1 minus 2x. And solving for x, we'll get x is equal to 0.0504. That's a little few extra digits than we need, but that's okay. Moles per liter. So this is the molar solubility of silver chloride when we have 1 molar ammonia present. Okay. Comparing that to what you can see, yes, this does increase the solubility of silver chloride. Okay. Yeah.
So, what's the reason that they is so big? It's gonna be like usually gonna be so big, or?
What's the reason that KF is so big? These complex ions actually form pretty readily in solution if they do form. We're gonna focus on complex ions that do form very readily. So if you go and look at the table in the book, they're all gonna have very large KF values. Yep. Any other questions? Yep. Easy? Let's try to see if I have any good examples here. Let's do a problem where we go back to, and I'm going to just wing this. That's scary. Questions before I make something up? All right. Let's go back to our fractional precipitation, no, the effective pH. There it is. Okay. Okay, so let's say we have a solution of manganese sulfate that's 6.9 times 10 to the minus 4 molar. To that solution, we're going to add sodium hydroxide, and it's going to, of course, increase the hydroxide ion concentration. And I want to know at what pH will manganese hydroxide precipitate. We have a KSP value for that salt. Let me get you started, I think. So I want you to work on this. I'm going to give you 30 seconds to try this to get started on your own. I want to see how you do. I want you to suffer a little bit, I guess. So we'll go with that. We'll have time to get it. Okay, so by asking at what pH will this solid start precipitating, we're effectively asking what hydroxide ion concentration. But we don't know anything about, we're effectively asking what H plus concentration, hydronium ion concentration. But we don't know anything about H plus in this example directly. We know about OH minus. So that's what I want you to look at. What this is essentially asking at what hydroxide ion concentration will manganese hydroxide precipitate. Does that make the question easier if you think about it that way? No. Okay, so in that case, let's look at, let me take an eraser here. Oops. Not erasing. Okay. Okay, so this is our equilibrium that's going to be important. Manganese hydroxide, yes. That is aqueous. So it's going to completely dissociate. Yeah. Okay, so now we have this equilibrium to worry about. We can write a KSP for this. KSP is going to be equal to the manganese concentration times the hydroxide ion concentration squared. Okay. We know the manganese ion concentration, right? So that completely dissociates. Manganese sulfate completely dissociates. So we'll have 6.9 times 10 to the minus 4 molar Mn2 plus. We know our KSP. The thing that we're looking for now is our hydroxide ion concentration. Does everyone see that? I think once you get to this point, then it's easy, right? But getting to that point is the really tricky part. Seeing what the question's asking. And I think that's going to be sort of the refrain for this portion of chapter 17 is figuring out what the question is asking is probably the hardest part. So doing lots of examples is going to be useful. Looking at those examples, figuring out exactly what they're asking, taking notes on how you know what they're asking, that kind of thing. That's going to be important. Okay, so like I said, we know our KSP, 2 times 10 to the minus 13. This is equal to 6.9 times 10 to the minus 4 times, we'll call OH minus X squared. So X is going to be equal to 1.7 times 10 to the minus 5. This is our hydroxide ion concentration. Now we do minus the log to get the POH. And I'll get 4.77. So then the pH, 14 minus that, is 9.23. Question? Okay. We'll be starting chapter 19 on Monday. Thermodynamics, thermochemistry, if you're looking for something to review to get ready for that chapter, I'm sure you are. Look for the chapter that has enthalpy in it, delta H.